Virtual metrology, 2 lectures on it, and this is the first. Here is the whole idea in one sentence. The tool streams hundreds of sensor readings during every run, and you throw almost all of it away. Virtual metrology is the claim that those readings contain the measurement that you did not take. For 3 lectures, we have been building charts on measurement. Today, we build a model that manufactures the measurement. And it is the first genuine machine learning system in this course, so everything we do today sets the pattern for the project. 6 things by the end of today. Explain why a fab measures 3 wafers out of 25 and what that choice costs. Say precisely what virtual metrology predicts. There are 3 neighboring ideas it gets confused with, and I want you to be able to separate them. Build a wafer-level feature table from the segmented sensor traces. This is the unglamorous part, and it is where most of the effort actually goes. Recognize P much greater than N and the name what it breaks. You have met this before. Lecture spree spent 2 slides on virtual metrology, and I promised we would come back. The claim was this: if sensor traces can predict the measurement, and they can because a trace is the record of what physically happened to the wafer, then predict it for every wafer. You get a CD number on all 25 wafers instead of 3 you could afford to measure at no metrology cost. And 3 things follow: bigger subgroups, so tighter limits and faster detection, feedback for the run-to-run controller on lots nobody measures, and a number available seconds after the run instead of hours after it. The warning is equally short. You are now charting a model output. If the model degrades, the chart moves and the process never changed. You have 2 things that can drift instead of 1. Every deployed model needs a control chart on its own residual. I said that was the most transferable idea in this course, and I meant it. Today is the left-hand card, how you build the thing. Next lecture is the right-hand card plus something worse, the reason the numbers on your notebook reports is usually wrong. Segment 1. Why virtual metrology exists at all. And I want to correct an assumption people arrive with. The problem with metrology in the fab is rarely the money. A CDSM is expensive, and so is an etcher, and nobody keeps etching. The problem is throughput and delay. There is never enough metrology capacity, and what you have gives you the answer late. Let us do the arithmetic of an actual sampling plan. A lot of 25 wafers. All 25 go through the etcher. All 25 get the same recipe. All 25 come out with a critical dimension that is now fixed and unchangeable. 3 of them get measured. Wafers 3, 12, 22. Say you pick positions that span the carrier. 22 wafers leave that etch with no number on them ever. They go into the next process step, eventually into a product, and the only thing you know about their critical dimension is what 3 other wafers did. So every decision you make about that lot, whether to release it, whether to adjust the recipe, whether the chamber is healthy, rests on 3 numbers out of 25, and you chose which 3, which means the answer partly depended on your sampling plan rather than on the process. Virtual metrology is about the other 22. 3 specific things that sampling plan costs you, and all 3 are things you already know how to reason about. Your charts are blunt. With n of 3 or 5 per lot, the x bar limits sit at the 3 sigma over root n. Small n means wide limits, and wide limits mean slow detection. Everything from lecture 2 about average run length applies directly. A shift you would catch in 5 lots at n equals 25 takes you 15 at n equals 3. Your controller is stalled. A run-to-run controller updates its correction when a measurement arrives. On an unmeasured lot, it has nothing to update with, so it holds its last correction and the drift keeps accumulating unopposed. If you measure 1 lot in 3, your controller is effectively running at a third of its design bandwidth. And you ship before you know. A queue in front of the CDSM is hours. By the time the number of lot 1 arrives, 4 more lots have gone through the same chamber on the same recipe. If something was wrong, it is wrong on all 5. None of these are metrology problems. Every one is a consequence of how few wafers carry a number. Here is the delay drawn out. Top row, the etcher running lots 1 through 6, one after another, fast, a lot every 20 minutes or so. Middle row, lot 1 goes into the metrology queue and waits, not because measuring is slow, measuring takes minute, but because there is one CDSM and a great many process steps that all want it. Bottom row, the number arrives. And look where it arrives. 4 more lots have already run. So the feedback loop we drew so neatly in lecture 3 with the controller updating after every lot is actually loop with 4 lots of dead time in it. Everybody who has taken a controls course know what dead time does to the loop. It limits how aggressively you can correct and it makes oscillations easy. The delay is what hurts more than the cost. So virtual metrology. Here is the definition and it is deliberately plain. Predict the measurement from the data you already have. No new sensor, no new tool, no change of the process. The tool is already streaming this and the historian is already storing it. The top row is today. A lot goes through the etcher, then 3 wafers out, 25 wafers go to CDSM and other 22 go straight on to the next step. Then hourglass. That queue is the whole problem. There is one CDSM and a great many process steps that all want it. So the measurement you eventually get is late and it describes 3 wafers. Slow, expensive in capacity and sparse. Now the same tool, same recipe, same wafer, nothing changed about the process. But the tool has been streaming sensor data the entire time. Chamber pressure, RF power, gas flow, hundreds of channels sampled every second, everything logged, everything stored, and in most fab never looked again unless something breaks. Feed those into a model and the model returns the predicted CD. 2 things change. It arrives in seconds rather than hours. It arrives in every wafer in a lot rather than 3. And the model itself is unglamorous. It is a regression, 1 row per wafer, few hundred label examples, a target in nanometers. Where do the labels come from? From the top row. Every real measurement you ever take is a training example, so your metrology history is your training data. And 2 parts are not alternatives. The top one teaches the bottom one. Same tool, same recipe, same wafers, only new thing is a model and everything it needs is already been logged. That is why this is the first machine learning project most fabs attempt. 3 things that live next door to virtual metrology. All 3 are real and useful. None of them is the same thing. The distinction matters when you read the literature. Inline metrology is a real sensor inside the tool making the real measurement. An interferometer watching a etch depth in real time, for instance, it produces measurements. Virtual metrology produces predictions of the measurement. If you can get inline metrology, take it, it beats a model. Soft sensing is the control engineer's term for inferring unmeasured variables from the measured one, usually through a physical model of the system. Virtual metrology is the data-driven wafer-level semiconductor-specific case of soft sensing. If you read the process control literature, you will find the same idea under that name, sometimes decades earlier. Fault detection asks whether the run was healthy, a yes or a no, or an anomaly score. That is what T-squared and SP did in lecture 3. Virtual metrology asks for a number in nanometers, which is a harder question and a considerably more useful answer because a number can be compared to a specification and fed to a controller. Virtual metrology predicts a quantity on every wafer in units of the specification is written. Segment 2, what you predict and what you predict it from, and a warning about how this segment fails. It is going to seem like bookkeeping. Choosing a target, listing input families, joining tables, no mathematics. That is the correct proportion. On a real virtual metrology project, this is where most of the effort goes, and it is where the project that fail already have failed before anybody fits a model. Not every measurement is equally predictable, and choosing a tractable target is the first real decision. Film thickness, post-CMP, post-deposition is the easiest. The measurement is optical, so it is cheap and densely sampled, which means plenty of labels, and the physics couple strongly to things the tool measures: polish time, motor current, slurry flow. Etch depth and etch rate are almost as good for a lovely reason. The endpoint trace is nearly a measurement already. Optical emission tells you whether a layer cleared. You are predicting a quantity a tool half observed. Sheet resistance sit in the middle, electrical stable and well sampled. Critical dimension is harder. The coupling to the chamber sensor is weaker and the tolerance is tighter, so the same relative accuracy is worth less to you. Overlay is harder still and structurally so. It involves two tools and it's inherently multivariate. We saw in lecture 3 that a single overlay number hides translation, magnification, and rotation. And defect count or yield is the hardest of all. Rare events, poor labels, a long causal chain between the tool and the outcome. So if you are choosing the first virtual metrology project in a fab, choose thickness or edge depth, not because the others are impossible, but because you want your first project to succeed and build credibility. Pick your target before you pick your model. It matters the most. 4 families of input, and the thing I want you to notice as we go, everything on this slide is already being logged. None of it requires a purchase order. Statistic from each step of each sensor: mean, standard deviation, slope, range, settling time. This is the bulk of the table by column count, hundreds of columns per run, and we will spend the next segment on how to compute them properly. The set points as actually run, which sometimes differ from the recipe as written: product and layer, chamber and tool identity, slot position. These are cheap and mostly categorical and frequently more predictive than the sensors, which surprise people the first time. Runs are clean, runs since preventive maintenance, runs consumable age, idle time before the run. This is the tool's memory and it is what drives a slow drift we spent lecture 3 trying to compensate for. And the one people leave out: what the wafer measured at the previous step. Routinely the single strongest predictor in the whole table and routinely absent because it lives in a different database owned by a different team. The engineering effort in a virtual metrology project is joining these 4 sources onto one row per wafer. The modeling comes after. It is the easy half. Let me show you why incoming state matters so much. Because the argument is visual. Outgoing CD plotted against the incoming CD for a couple of hundred wafers. Correlation is about 0.96. The outgoing value is mostly the incoming value, which makes physical sense. The etcher removes a certain amount of material. Whatever comes in plus the removal is what goes out. If the incoming distribution is wide, the outgoing distribution inherits that width. Nothing the chamber does changes it. Now look at the removal. Incoming minus the outgoing. Standard deviation of 0.4 nanometers against 1.5 nanometers on the outgoing CD. The removal is what the tool actually did. It is the quantity the sensor traces are a record of, and it varies about 4 times less than the thing you were originally trying to predict. So predict what the tool did rather than what came out. Smaller target, cleaner target, and the traces generally know about it. Let us write that down because it is the most useful single trick in this lecture. CD out equals CD in minus removal, and the tool controls only the removal. If you predict CD out directly, your model has to reproduce the incoming distribution as well as the tool's behavior. Most of the variance you are asking to explain has nothing to do with the chamber, and the sensor traces know nothing about the incoming CD. That variance is therefore unexplainable from your features, and your R squared absorbs the whole loss. You will look at a mediocre R squared and conclude that sensors are uninformative when in fact you asked the wrong question. If you predict the removal, the target is exactly what the tracers record. Smaller spread, stronger coupling, and a physically meaningful quantity that a process engineer can argue with. Then add the incoming measurement backward afterwards. The same answer, much better model. This requires the incoming measurement to exist, which brings its own sampling problem. You may not have measured this wafer at a previous step either. In practice, you use the lot mean or a virtual metrology prediction from the previous step, and you accept the extra noise. Choosing the target well buys you more accuracy than any change in the algorithm. I want it on a slide because people picture something more exotic. 1 row per wafer, 1200 rows from the dataset you will use for homework. The identifiers on the left, wafer, lot, chamber, those are for joining and splitting, never for modeling. I'll come back to that. Then chamber state, then the sensor block F0 through F39 in our dataset. Then a lot level block F40 through F59. Features that are constant across every wafer in a lot is like an incoming lot measurement or a square time or a queue time. Then a nuisance block F60 through F119, which is mostly noisy because a real table contains plenty of columns that turns out to be useless and you do not know which in advance. And on the far right, the target, present on 465 of 1200 rows. Every dash is a wafer that ran and that has a full set of features and that has no measurement. Every dash is a row in a virtual metrology exists to fill in. That is the whole supervised learning setup. Rows with the label train the model. Rows without labels are what you built it for. And now the part that stalls these projects, which is the plumbing rather than the modeling. Trace data is keyed by tool, chamber, and time step. Metrology is keyed by lot and slot. To connect them, you need the tool's own log, which slot ran when, and the slots map are wrong more often than everybody admits, especially after a wafer has been reworked or a carrier reloaded. The tool clock, the MES clock, and the metrology clock disagree. Seconds, usually minutes, sometime. Join on the wrong one and you attribute a trace to the neighboring wafer. Your model that learns a relationship is off by one, which degrades quietly rather than failing loudly. A reworked wafer has two traces, one measurement. A lot split across two chambers has two genealogies, both corrupt, a naive join, and neither raises an error. Sensor calibration change. Recipe revisions rename steps, so your step-based segmentation silently starts summarizing the wrong window. A column called pressure can mean different things in 2023 and 2025. Budget most of the project for this. I know this is unsatisfying. You came here for the machine learning, but a clean table with rich regression beats a dirty table with transformer every single time, and the second one is much harder to debug. If you take one practical thing from this lecture, take that. Segment 3, from traces to features. Lecture 3 gave you the pipeline in one slide. Segment by recipe step, summarize each window, chart the summaries. Today I want to show you what it takes to make that actually work, because each of those three words hides the decision. Here is one sensor on one wafer, chamber, pressure 60 seconds. The recipe has phases and they are shaded. Palm down, ramp, main edge, the long window in the middle, vent. And they are not equally informative. Palm down tells you about the vacuum system. Vent tells you about the exhaust. The main edge window is where the wafer is actually being processed, and that is where the signal about CD lives. Which means you cannot take the mean of the whole trace. That would average the edge window together with the palm down, and the answer would depend mostly on how long the palm down happened to take that day. So segment first, then summarize the window you care about. 4 numbers here from the main edge window. The mean, which is the level it held. The standard deviation, which is how steady it was. Slope, which is whether it drifted during that step. The range, which catches the worst excursion. 4 numbers, 1 sensor, 1 step, multiply by 300 sensors, 5 steps, you begin to see where the column counts comes from. Now the first thing that goes wrong. Several run of the same recipe plotted on their raw clocks. Look at where the vent step begins. It is a different second on every run, because the steps are not fixed in duration. An endpoint control H ends when the optical signal says the layer cleared, which takes a very slightly different time on each wafer. That is the recipe working correctly. But it means second 35 is inside the main edge on one wafer and inside the vent on the other. If you compute the mean of seconds 30 to 40s across runs, you are averaging different physical phases together, and the feature you produce is dominated by step length variation rather than anything about the wafer. So align first. The simple version, which is what is drawn here is to normalize within each step. Resample every step onto the same number of points. Now index 50 means same physical moment and each wafer. The more careful version is a dynamic time wrapping which aligns the shapes rather than just the boundaries. Worth it when the step has internal structure you care about. Averaging across ragged runs manufactured noise, and then you spend a month trying to model it. Chamber state, and this one earns its slide. This is the quantity we are trying to predict plotted against run index across 1200 runs. And the dashed lines are the chamber cleans. Look at what happens after each clean. The level jumps and then drifts back. That is whale chamber condition. Polymer builds up on the walls, changing the effective chemistry, and the clean resets it. None of that is visible in any single sensor reading. The pressure looks the same on the run 2 and run 200. What differs is accumulated history. And you capture it with one integer, runs since clean. Probably a second run since PM. In my experience, and this matches the published work, that those two integers frequently add more predictive power than 50 sensor columns. They are free, they are in the maintenance log, and they are often missing from the feature table because the mainstream log lives in a different system. Ask what the tool remembers and find a column for it. Two more small features, both free and both commonly missing. The first in the lot is different. Here it runs about 0.17 nanometers lower than the rest, and that is a real and repeatable effect. The reason is thermal. The chamber has been idle between lots, so the walls are cooler. The first wafer conditions the chamber for the ones that follow, and it pays for that with a slightly different result. You capture the whole effect with a single binary column. Is this slot 1, yes or no? The slot position more generally. Position in the carrier correlates with thermal history and with the handling order. It costs you one integer and it shows up in the selected features, often enough to be worth including every time. Both of these came from asking a process engineer what they thought mattered. Neither would be discovered by a model searching a table that did not contain the column. Domain knowledge enters machine learning project as feature columns. That is the mechanism. Ask which conditions people think matter and then find a way to encode each one. One more family and it is a callback. A wafer is not independent of the wafer before it. The chamber that runs the last 5 wafers is the chamber running this one and its state carries over. So encode recent history. The gray line is the individual value and the tail line is the EWMA over the last few runs with a lambda of 0.25. You have seen that exact formula. It is in the EWMA from lecture 3. The run-to-run controller, same lambda, same recursion. The difference is what we do with it. In lecture 3, the EWMA drove a correction. Here it is a column in the feature table and input rather than the action. And it gives the model something a single wafer snapshot cannot, a sense of where the process has been heading. A wafer at 45.3 on the way up is in a different situation from a wafer at 45.3 on the way down. Encode the time structure instead of hoping the model discovers it. With 400 labels, it will not discover it. And now the problem this whole field is organizing around. Multiply it out before you write any modeling code. 300 sensors, 5 recipe steps, 6 statistics per window, 9,000 columns. How many label wafers do you have in your dataset? 465, which sounds small until you realize it represents about 18 months of production metrology at a realistic sampling rate. You cannot simply go and get more. You would have to wait. 19 columns for every row, and it is the wrong way around. This is the opposite of the situation most machine learning intuitions come from. Image classification has millions of examples and a fixed input size. Here the inputs outnumber the example by an order of magnitude, and the examples arrive at a rate fab measures the wafer. Statisticians write this as P much greater than N. It is the defining constraint of virtual metrology, and every choice for the rest of the lecture follows from it. So what does P greater than N actually break? 70 label wafers in the training set, Then I get columns, 5 features, 10, 20, up to 64. Every time I fit ordinary least squares and score it 2 ways. The gray line is R squared on the training data. It climbs to 1. With 64 columns, 70 rows, the model reproduces the training set essentially perfectly. The red line is the same model on held out data. It falls off a cliff at 64 columns. It is below -3, which means the model is worse than predicting the mean and dramatically worse. With enough columns, there are many combinations that fit your 70 points perfectly, and they disagree wildly everywhere else. Least squares pick one of them essentially arbitrarily, and the one it picks is the description of your noise. The teal line is the ridge regression on the same data, same column. It stays high, one penalty term, the collapse disappears. So the answer to too many columns is a constraint on the coefficient. Every method in the next segment is a different way of imposing one. 4 pieces of housekeeping. They sound like footnotes. Each one has cost somebody a project. Pressure in millitorr, power in watts, flow in SCCM. Orders of magnitude apart. Every penalized or latent variable model is scale sensitive. Reach penalizes large coefficient, and what counts as large depends on the units. So standardized. And standardized inside the cross-validation tool, never before it. If you compute the mean and standard deviation and all your data and then split, information from the test has leaked into the training set. That is the small leak today and the large one next lecture. A sensor that sticks at its last valve looks perfectly well behaved on a plot and carries 0 information. Our dataset has 1 planted, and finding it is the homework problem. Check variance on the rolling window, because a sensor that was fine for 6 months and died in July will pass a one-off check on the whole history. Around that aborted mid-recipe produces a trace, a feature row, and nonsense. Filter on recipe completion before anything else touches the data. And keep identifiers out of the model. Wafer ID, timestamp, run index, every one of them will predict beautifully on a random split and mean absolutely nothing. That last point is the seed of next lecture. If the column encores when rather than what, it belongs in what you split the data, not in the model. Segment 4, models in the order you should actually try them. And the order matters more than the list. Start with something you can defend to a process engineer and escalate only when the data gives you a reason to. Before any model at all, the baseline. Here is the simplest possible predictor. To guess this wafer CD, use the previously measured wafers CD. That is the whole model. No features, no fitting, one line of code. Navy is measured, gold is the previous measurement shifted toward one step. It tracks reasonably well because the process is auto-correlated. Consecutive wafers really are similar. RMSE of 0.6 nanometers, R squared of 0.61. 61% of variance from a model that knows nothing. So if you build a 9000 feature gradient boosting machine and report R squared of 0.65, you have done a great deal of work to add 4 points over a one-liner, and somebody should ask you whether it was worth the maintenance budget. This is a general habit, and I want you to carry it into your projects. Every predictive claim needs a trivial comparison chosen honestly. For time series, the usual honest baseline is the same as last time. For classification, it is always predict the majority class. Any model that cannot beat this is not a model. Compute it first, and so you cannot fool yourself later. 2 ways to survive too many columns. Both add a penalty on the size of the coefficient. They differ in the shape of the penalty, and the difference in behavior is dramatic. Reach penalizes the sum of the squared coefficient. As penalty weakens, going left to right, and the coefficient grows smoothly out from 0. Every one of them is non-zero at every setting. So reach shrinks everything and keeps everything. It handles correlated columns gracefully. If 2 sensors carry the same information, reach splits the coefficients between them. Lasso penalizes the sum of absolute values. Look at the difference. Coefficients sit at exactly 0 until the penalty weakens enough, and then switch on one at a time. In the middle of that plot, 36 of a 322 are non-zero. Rest are exactly 0. So lasso selects, it hands you the subset. With correlated columns, lasso is unstable. It picks one of the correlated pairs somewhat arbitrarily, and slightly different dataset picks the others. So if you care about which sensor, treat the selection as indicative rather than definitive. Elastic net mixes two penalties and gets sum of both, selection with correlated groups entering together. In practice, it is a reasonable default when you are unsure. Now, the reason lasso arm seats keep in a fab specially, and it has a little to do with accuracy. Lasso keeps 22 of 120 features. These are the 16 largest. Each bar is a named column with a physical meaning, a particular sensor in a particular recipe step summarized in a particular way. That list is a conversation. You can walk into a process engineer's office with 16 names and ask whether they make sense. Sometimes they say yes and you have gained confidence. Sometimes they say the gauge has been unreliable since March and you have learned something no cross-validation would have told you. A model that uses all 900 columns cannot have that conversation. It may well be more accurate. It will also be harder to trust and harder to debug when it drifts, and much harder to get approval to put in the loop. One thing to notice before we move on, look at the colors. A lot of those selected features are gold and a lot level block. Hold that thought. It comes back on slide 34 and again next lecture. A model that names 20 sensors gets acted on. A model that names 9,000 gets admired and ignored. PLS, partial least squares regression. If you remember one method from today, remember this one because it is the workhorse for virtual metrology, and the reason is exactly P much greater than N. You start with 120 features, 9,000 in a real fab, too many to estimate coefficients for each. So compress. Find a small number of latent components, each a weighted combination of the original features. 6 here, 8 in the model, we will fit. Then regress the target on the components, 6 or 8 coefficient instead of 9,000. And here is what makes PLS the right kind of compression. It chooses the direction that vary with CD, not simply the direction that vary most. Because the largest source of variation in a set of chamber sensors is often something you do not care about. A pressure controller, hunting, mass flow controller with a noisy valve, that variation is large and it has nothing to do with the wafer. A method that compresses by variance alone will spend its first component describing it. PLS looks at the target while choosing direction, so it skips that. Estimate 8 numbers from 456 rows and you are on a comfortable ground. Estimate 9,000 and you are in a disaster we saw 2 slides ago. Compression is what makes the problem well posed. PLL compresses in that direction that matters. Let's make that concrete against something you already know because you met PCA in lecture 3. 2 sensor features, color is CD, red high, blue low. The gray arrow is PCA's first direction, the direction of greatest variance. It runs left to right because feature 1 has much larger spread. And notice, as you move along the gray arrow, the color barely changes. That direction has a great deal of variance and almost no information about CD. Navy arrow is PLS first direction, the direction of greatest covariance with CD. It runs bottom left to top right, straight up the color gradient, has much less variance along it, all of the signal. So PCA looks at X alone, it needs no target, which is exactly why it works for monitoring. The T-squared and SP charts in lecture 3 were built on unlabeled data, and that is their great advantage. PSL looks at X and Y together, it needs labels, and in exchange it aims the compression at the thing you want to predict. For monitoring, use PCA, for prediction, use PLS. Same machinery, different objectives, and the objectives is the whole difference. How many components? This is the one hyperparameter PLS really has, and you choose it by cross-validation rather than by intuition. Cross-validated RMSE against the number of components, it drops steeply from 1 to about 4 and then flattens, then very slowly worsens as you add more. The minimum is 9 components, RMSE of 0.325. But look at how flat the region is. 4 components gives you essentially the same error as 9. And the exact location of the minimum is noisy, reshuffle the folds and it moves. So take the simplest model in the flat region rather than the exact minima. 4 or 5 components here, you lose almost nothing in accuracy and you gain a model that is more stable and more interpretable and less prone to having learned something fold specific. Notice the teal dashed line at 0.22 nanometers. That is the gauge noise on these labels. No model can get below it for reasons we will make precise next lecture. We are at 0.325 against a floor of 0.22. That is genuinely close. Choose the number of components, do not guess it, and prefer the simplest model that is statistically indistinguishable from the best one. So here is a working virtual metrology model, PLS, 8 components, 465 labeled wafers, 5-fold cross validation. Predicted against measured, the dashed line is a perfect agreement. R squared of 0.881, RMSE of 0.333 nanometers. Put that in context, the specification window on this parameter is 4 nanometers. Our prediction error is a third of a nanometer, about 8% of the window. And the metrology tool itself has 0.22 nanometer of noise, so we are within about 1.5 times the measurement error of the tool we are trying to imitate. And here it is in time order for the first 170 labeled wafers. Navy points are measured, the goal line is predicted. It tracks the real excursions, the run up around the wafer 150 and the drop after. If you build this in a notebook, this is the point at which you should write the email. The plot looks right, the R squared is high, the RMSE is close to the physical floor. Hold that filing, we are going to come back to this exact number and to know how it was computed. Before we celebrate, read the model. This is a habit worth having. Look at what the thing is learning on. These are the weights on the first PLS component, 1 burp feature. Teal is the sensor block, gold is the lot level block, gray is the nuisance block. The nuisance block is quiet, which is reassuring. PLS correctly ignored 60 columns of noise. And look at the gold block. The lot level features dominate the first component. The first largest weight in the model are on the feature that are constant across every wafer in the lot, which raises a question. If a feature is identical for all 25 wafers in a lot, what is it telling the model about an individual wafer? It is telling the model which lot this is, and if the model knows which lot a wafer came from, it has already seen other wafers from that lot with this measurement and then some of the impressive R squared in the model, recognizing a lot rather than predicting a wafer. I'm going to leave that hanging because unpicking it properly takes the first 25 minutes of the next lecture. Hold on to this observation. It is the thread that unravels the whole result. One more model worth knowing, and I want it here for a reason that is operational rather than statistical. Gaussian process regression. It produces a prediction and an internal interval around the prediction. Gold dots are wafers you measured. The navy line is the prediction. The shaded band is 95% prediction interval. Look at the pink stripe in the middle where there is no training data. The band widens substantially. The model is telling you in its output that it is guessing here. That is genuinely useful property in the fab, and it is not about accuracy. The model here, the model with an interval can be told to abstain. When the interval is wide, the right action is to send the wafer for a real measurement rather than trust the prediction, which turns a fixed sampling plan into an adaptive one. Measure the wafers the model is the least sure about and skip the wafers it is confident about. That is a large operational gain and it becomes a whole segment next lecture. Gaussian processes scale poorly, roughly the cube of the number of training points, which for 475 wafer is irrelevant, and for 100,000 it is fatal. There are approximations and you can get intervals from other methods too, with quantile regression and conformal prediction. A model that reports how sure it can be trusted more carefully. That is worth something separate from being accurate. Two more options and honest guidance on each. Gradient boosted trees. On a wafer level feature table like ours, usually the stronger performer. It picks up interactions and monotone but non-linear effects without being told they exist, and it needs almost no pre-processing. It cannot extrapolate outside the range of training data. A tree ensemble returns the value at the edge of that range confidently and with no indication that anything unusual happened. In a process that drifts, which is every process in this course, you leave the training range routinely. Neural networks on raw traces. One-dimensional convolutional network learns shape features directly, overshoots settling behavior, ramp curvature instead of you specifying the window, means, and slopes. That is genuinely appealing because your hand-designed statistic may be throwing away the shape information. And here is what stops it: labels. With 465 measured wafers, a CNN on raw traces will lose to PLS reliably. Visit it at tens of thousands of labels or use self-supervised pre-training on millions of unlabeled runs and fine-tune on the few hundred labeled ones. That last recipe is the current research frontier, and it is a reasonable project topic. Everything side by side, same 456 wafers, same 5-fold cross validation, RMSE in nanometers, so lower is better. Baseline is gold at 0.6, reach at 0.319, lasso at 0.338, PLS with 8 components is 0.333, gradient boosting at 0.291, and the gauge noise floor is 0.22. First, every model comfortably beats the baseline, roughly a factor of 2. So there is a real signal in these traces, and virtual metrology is doing something. Second, the model are all close to each other. Reach, lasso, and PLS are within about 5%. The choice among them matters much less than the data preparation we spend in the middle of the lecture on which is the honest lesson, and it is not the one most machine learning courses teach. Third, gradient boosting reaches 0.291, about 1.3 times the gauge noise. For predicting a measurement without taking it, that is a good result. Notice which decisions move the number. Target choice, feature quality moved, algorithm choice barely did. So we have a working model. Let me put the headline on the slide and then take it apart. PLS 8 components, R squared 0.881, RMSE 0.333 nanometers. This is what we would report, cross-validated on 465 wafers against a physical noise floor of 0.22. By standards of a good deal of published virtual metrology work, this is a solid result and it would pass review. And here is exactly what we did. Took the 465 labeled wafers, shuffled them, split into 5 folds, trained on 4, tested on the 5th, 5 times around, averaged. That is a textbook 5-fold cross-validation. It is what the Scikit learn does by default. It is what every tutorial shows. And the problem is the shuffle. Wafers from the same lot ended up in the training set and the test set. So when the model predicted a test wafer, it has already seen its neighbor from the same carrier with their measurements. And remember slide 34 where the lot level features dominated the first component. The model has a lookup table. Wafers from the end of the year ended up in training for wafers from the beginning. The model was allowed to know the future. Next lecture, we evaluate the same model, same feature, same algorithm, same data with splits that respect lots and respect time. R square falls for 0.881 to 0.593. And here is the number that actually matters, scored on the same held out wafers. The one-line baseline gets an RMSE of 0.573 nanometers. The model gets 0.555. 3% better. Everything we built today by 3% over a predictor that ignores the sensors entirely. 42% advantage we thought we had was an artifact of how we split the data. Nothing we do today was wasted. The pipeline is right. The features are right. PLS was the right method. What was wrong was how we asked whether it worked, which is the subject of the next lecture, and it is the more important half. 6 problems. And the datasets are on the course site. 4 files, features, labels, events, and a subset of raw traces. Build the features yourself from the raw traces, segment by recipe step, compute the mean, standard deviation, slope, and the range per step per sensor. and then compare your columns against the one I supplied. They will not match exactly, and understanding why is the point. Compute the baseline before anything else, the reach fit lasso PLS random. Report random 5-fold RMSE for each. You should land close to the numbers on slide 37. Choose the number of PLS components by cross-validation and justify taking the simplest model in the flat region rather than the exact minima. I want the argument written down, not just the number. List the 10 largest lasso coefficient and say which block they came from. If you answer the lot level block, tell me what that implies. You will need the answer for the next lecture. Given the gauge sigma of 0.22 nanometers, which is the smallest RMSE any model would achieve in these labels, derive it, do not guess it, they say how close you got. One column stops varying partway through. Find it and find the run where it stops. It takes 3 lines of code and it is kind of the check nobody runs. Keep the notebook, next lecture will reevaluate the same model and numbers change, and it is far more instructive if the first set of numbers is yours.